And our next speaker is Nisheeth Vishnoi coming from Yale, presenting on centralized selection with preferences in the presence of biases. This is joint work with Elisa, Celis, Amit Kumar, and Andrew Shu.
So my slides are pretty simple. In case this is not working, whenever I raise this, if somebody can, yes, there's no animations. It's just slide after slide after slide. Okay, thank you everyone for coming. This is a talk about centralized selection process, which is prevalent in college admissions in the presence of where there are preferences of the candidates in the presence of biases. This is joint work with Elisa Celis from Yale, Amit Kumar from Indian Institute of Technology in Delhi, India, and Andrew Shu also from Yale. So this is the problem that we are considering. So imagine that there are candidates, and we think of candidates, let's say for this talk, divided into two demographic or socially salient groups, G1 and G2. There is an evaluation process. Think of it like an exam, specifically in one of the major exams in India called the IIT exam. All candidates have to appear and give the same exam, and then the scores of these exams are used to determine eligibility into the different IITs. So there are multiple institutions. These institutions have capacities. Without capacities, this problem would not be interesting. And at the same time, the candidates, especially those who are selected, have preferences over the institutions. The goal is to find an assignment here which maximizes utility. So that's the traditional goal of the problem, where we select candidates who have the highest score in this exam. Such exams are also prevalent in China and other venues. If you know other examples, please tell us. So what can we do algorithmically? Well, the naivest thing is to do this Gale-Shapley algorithm, which has been used. The Gale-Shapley algorithm is more general in the sense that it allows each institute to have its preferences over the candidates, but here each institute generates the same preference list based on the evaluation it receives from the centralized admissions test. So it's a special case of Gale-Shapley. The key starting point of this study is that, and I think this point has been raised in the couple of talks before this talk, is that these evaluations might be biased in one way or the other, whether these are systemic biases with respect to certain groups or implicit biases. Doesn't really matter, but it has been shown in numerous occasions, including the context that we study, that certain groups, the scores reported for certain groups are not the right thing that should be evaluated. So the key point, from this slide, I'm not going to repeat much of what you saw in the previous two talks, but the key point is that the measured estimate is not accurate, especially for one group compared to the other. And the question that we would like to study is what happens to different types of fairness metrics in this setting. So a little bit more mathematically, we consider N candidates that apply to P institutes. The institutional capacities are K1, K2, and so on. Each candidate has a latent or the true utility, which is what we should be observing. It is denoted by UI. And each candidate also has a preference over the institutes, which is a ranking, and we denote that by sigma I. We think of candidates in group 1 as the advantage group and candidates in group 2 as disadvantage group. The assumptions for this talk are that all utilities are drawn from the same distribution irrespective of the group. They are not the same, but the distribution is the same, and all preferences are also drawn from the same distribution. We are going to appeal to a model of bias which was studied by Kleinberg and Raghavan in 2018. It's a very simple model, but very helpful in trying to understand and perform theoretical analysis of some of these algorithms. It says that there is some unknown parameter beta, think of it as a number between 0 and 1. The observed utilities of candidates from group 1 is what the true utility is, but for the group 2, you observe a discounted utility, which is the true utility multiplied by this factor beta. Keep in mind, this is capturing a very complex process, so we don't expect to know beta. Otherwise, we could just nullify the effect of beta and get to know the true utilities. So what are our fairness metrics? The fairness metrics that we consider are two, representational fairness and also preference-based fairness. And besides that, we also consider a notion of utility. One can look at the utility obtained, utility of an algorithm is the sum total of the utility of all candidates that have been selected, normalized appropriately. And in terms of fairness, I want you to focus on the third one, which is preference-based fairness. And this is just then looking at the disparity with respect to this performance measure. Since everything is identical, the true utilities are drawn from the same distribution, the preferences are drawn from the same distribution, this number ideally should be 1. So the first question we can ask is what happens to the Gale-Shapley algorithm if we use it without, without cognizance to biases for these metrics. So this is our first set of results, which is essentially establishing the limitations of the Gale-Shapley algorithm in the presence of such biases. The theorem kind of looks complicated, but let me just kind of tell you roughly what it's saying. It's saying that the standard Gale-Shapley algorithm, which is denoted by A sub st, representation fairness of it, which is this R of A sub st, goes down as beta goes down. So in fact, it's just kind of linearly going down with beta up till some small noise. It increases. Same thing for the preference-based fairness. So in particular, these results show that as this systemic or implicit bias is increasing, we see increasingly the disparity between two groups, where one group tends to get candidates from one group tend to get more and more of their first choice, whereas candidates from the second group end up getting their lesser choices, not the first choice. So then the question is, can we design some interventions for this? I mean, how do we change the algorithm? And this is, I think, can we go one slide back? I think we skipped, they skipped one. Yeah, this is good. So we define, if you look at the second block, we define an algorithm which is essentially a version of Gale-Shapley, where we now break the population and think of the population just as into two different groups and consider two instances of this assignment problem where the capacity K sub L at the Lth institute is broken proportionately depending upon the groups. So we compute two different allocations, and because the capacities have been broken appropriately, then when we merge the two allocations, we do not violate the capacity constraints. So for this algorithm, which is a pretty straightforward algorithm that you can imagine, we can show that the fairness metrics and the utility all tend towards 1 irrespective of the bias parameter, and as these size of the problem goes to infinity. So if you ignore that term 1 minus order of that thing inside the bracket, which is going to 0 as k is going to 0, or k is going to infinity, then in all of these metrics we have the desirable properties of this algorithm. So now one observation for people who care about certain properties of the Gale and Shapley algorithm, specifically stability. We cannot expect stability. I mean, it's not even clear how to define a notion of stability here, because we are working with observed utilities. But we can show that in each group the allocations are stable, Pareto efficient, and strategy proof, and so on, which are standard properties of. This is not surprising given that we break the problem into two parts and execute the algorithm. Next slide, please. Okay, so just a quick word about proof ideas. I think both of these proofs rely on some new properties of the traditional or the standard Gale-Shapley algorithm, in particular some algorithmic stability properties. So for instance, the second result relies on this property of Gale-Shapley, which tries to understand what happens when you change the capacity of an institute by 1. How do the allocations change? This is a question that you could have asked irrespective of this work, and the answer turns out to be intricate. It depends, it depends upon the distributional assumptions in the paper. But what we can show is that this change is not much. So if there are, for example, 2 institutes, and if I change the capacity by 1, then of any institute, then the allocations change by 2 in how the allocations are made. Similarly, there is a Lipschitz property or a stability property with respect to the change in preferences that is crucial to the proof for result 1. So I think these properties that we discovered while proving a result should be of independent interest to people who are generally interested in Gale-Shapley and college admissions problem. Next slide, please. So we also conduct some empirical results where we show, we go back to the context, which is this Indian Institute of Technology joint entrance exam, the IIT JEE results, and we show a distinct advantage that this algorithm that we propose has. So in particular, P sub 1, P sup 1 just means the fraction of candidates with respect to the first. So P sub 1, P sup 1 is the preference-based fairness for where we are only looking at the top preference. How many people get their first preference, how many people versus from group 1 versus how many people get the first preference from group 2. And that raises up from 0.25 to 0.90. We also looked at several variants. So the paper has many different empirical results that you can look at. And overall, it seems like the simple adaptation of this algorithm, the Gale-Shapley algorithm, is also useful and does well in practice, where many of the assumptions that we made in the theoretical results may not hold. Next slide, please. So I'll conclude by just saying a few things. So, well, evaluation processes are everywhere. We saw in the last two talks, they were all about evaluation processes and how different types of noise or bias can affect the outcomes. We considered a specific model of bias in evaluation processes. And our main contribution theoretically was to analyze Gale-Shapley algorithm in the presence of such biases. In particular, we discovered new stability properties of this algorithm, algorithmic stability properties of this algorithm, which may be of interest. We propose a new algorithm, which we are now working with the Indian Institute of Technologies to study the feasibility of actually using them in this exam. I guess some of the future works could be extending our work to the setting where there is not a single score that is being used. This specifically applies to many of the US college admissions where there are a couple of criteria, they're not, and so coming up with good models of correlations and analyzing a more complicated setting would be of help and usefulness to the context in the US and many other places, I believe. With this, I'll thank you. If you want to look at the paper, it's available. The code is also publicly available. Thank you.
Hi, thanks so much for the talk. Just upon first hearing this, it seems that one of the reasons that this algorithm works so well is because of what you hear described as the IID assumption for utilities across groups. The group latent distribution is drawn from the same distribution.
That's right.
But if we were considering a setting where we didn't necessarily expect that different groups would have the same latent distribution, where maybe a group average would be expected to be lower, but we didn't know how much of that would be because of a bias or because of an actual, on average lower performance that we would expect from the group. How does that affect this algorithm? It seems like then the optimal utility would be harder to reach, right?
Yes. In fact, that question, that's a great question. It already makes sense in the simple setting where there is only one institute. So this is the vanilla selection problem, where I have n candidates, I look at their scores, and I just want to select the top K. Mm-hmm. And for that, already the problem that you're raising will arise. So we haven't studied this because we know that problem already arises in the most basic selection, special case of this. But thank you for asking this question.
Great talk. So
Thank you.
I have a question. Here you have a unique stable matching, right? Because it's a...
That's correct.
Oh, so
Yes.
Do you have any idea if any of these results can extend when you have
Yes.
multiple preferences? Does it have anything with the core polytope in particular? Stability?
Sorry, what's your last?
So my question is the stability.
No, I understood so the stability is because of the unique matching. Yes. So, but the second part I did not understand.
And then the second part was that, is there an interpretation of the results for maybe more general setting, in the sense that I look at the core of the cooperative game and see how does changing the capacities would change the core polytope?
So I haven't thought about it, but it's a great question, and we can talk offline. But yeah, that's right. I think one of the things that makes this result works, as Rad pointed out, is that there is only one stable matching. It's unique, and so it's very easy to understand mathematically. In fact, this last bullet point here, where I'm talking about future work, which we are thinking about currently, the moment we have different institutes having different rankings, this property is gone, and then all of these things disappear. So we are in the process of understanding this. We don't have, results that I can present here, but yes, we are actively thinking about it, and would be happy to chat with you more. Thanks.
Sounds good. Thank you.
Okay, one more round of applause for Nisheeth and all our speakers. Thank you so much for bearing with us, to all of you.